deep neural networks. They're pretty much the engine behind all the modern AI we see today, from recognizing your face in a photo to translating languages on the fly. And they are incredibly powerful, but for years, they had this hidden catch, a really fundamental problem that made them almost impossible to train. So let's get into it and unpack the mystery of why making a network deeper isn't as simple as it sounds.
At first glance, the logic here seems totally straightforward. On the left, you've got a shallow network, just one hidden layer. On the right, a deep one with a bunch of layers. Now you'd think, pretty intuitively, that adding more layers, more depth, would let the network learn more complicated stuff and just get more powerful. But for a long time, researchers were finding that, well, that's not what was happening. In fact, sometimes it made things worse.
And right there, that's the central paradox we're going to explore. If deep networks are supposed to be the more capable ones, why did trying to build them often lead to failure? What was going on under the hood that was basically sabotaging their own ability to learn?
Okay, so to really get a handle on the problem, we first have to appreciate why everyone wanted all this depth in the first place. Let's take a look at why we even want to build these deep architectures. A great way to think about it is to picture an electrical circuit, right? If you want to multiply two numbers, you don't just build one giant, crazy complex gate. No way. Instead, you design it in layers. The first layer does simple stuff, like adding individual bits. Then the next layer uses those results to add whole numbers. And then a final layer pulls all that together to do the actual multiplication. See? It's a hierarchy, a layering of simple ideas to create a complex one.
And that's exactly how neural networks are supposed to work. The very first layer might look at an image and learn to spot really basic things, like little edges or curves. The next layer then takes those edges and learns how to combine them into something more complex, like an eye or a nose. And then a layer after that might put it all together to recognize a whole face. This layered understanding is the whole theoretical magic of deep learning.
So, if the theory is solid, the problem has to be in the execution. So let's take a quick look at how these networks actually learn, because this is where we start to see the cracks forming.
Okay, so in a nutshell, training is really just a sophisticated game of trial and error. The network takes a guess at something, it checks how wrong it was, we call that the error, and then it tweaks its internal connections, its weights, to make a slightly better guess the next time around. The algorithm that tells it how to make those tweaks is called gradient descent.
Probably the best analogy for gradient descent is to imagine you're standing in a huge, foggy valley, and your goal is to get to the absolute lowest point. You can't see the bottom because of the fog, but you can feel the ground right under your feet. You can tell which way is downhill. So what do? You take a small step in the steepest downhill direction. Then you do it again, and again, and again. Each one of those steps is the network adjusting itself, getting closer and closer to the bottom of the valley, which for us means the lowest possible error.
Now that whole process sounds pretty foolproof, doesn't it? Just keep taking steps downhill. Easy. But with deep networks, something really strange started happening to that downhill signal. It just started to fade away.
And this is the million-dollar question. If the goal is simply to follow the slope down, how could a network with more layers, more chances to make adjustments, actually get lost? Where is the signal breaking down?
And this visual, wow, this just lays the problem out perfectly. What you're seeing here is the learning speed of different neurons. The bars inside each neuron show how fast it's updating itself. Now just look at the difference. The neurons in that later layer, on the right, they're learning like crazy. The bars are huge. But the neurons in the early layer, on the left, they're barely changing at all. Their bars are absolutely tiny.
So what's happening is this. During learning, a correction signal gets sent backwards through the network. That signal is strong for the last layers, but it gets weaker and weaker and weaker as it travels back. By the time that signal gets all the way back to the earliest layers, it's just a whisper. Those early layers, the ones that are supposed to learn the most basic, fundamental patterns, are basically frozen in place. They're left in the dark.
And this phenomenon has a name. You might have heard of it, the vanishing gradient problem. That downhill signal we talked about, that's the gradient. And in these deep networks, it can shrink exponentially on its journey backwards, until it all but vanishes, starving those crucial early layers of any information they need to improve.
But here's the thing. A vanishing signal is only half the story. The problem is actually much bigger. It's about a fundamental instability in the entire learning process.
Because you see, sometimes the exact opposite happens. Instead of fading away, the signal can get amplified as it travels back, growing exponentially huge. We call this the exploding gradient problem. So you've got these two ways to fail. With vanishing gradients, the signal is like a whisper at the end of a really long hallway. It's just too quiet to hear. With exploding gradients, it's like that awful screaming feedback you get from a microphone. It's so loud and chaotic, it just completely overwhelms everything.
And this is where Michael Nielsen, the author of one of our source materials, really nails it. He says the core issue isn't just one or the other. It's that the gradient is fundamentally unstable. That learning signal is the result of multiplying a bunch of numbers together, one for each layer. And trying to keep that product stable over many, many layers is incredibly hard. It means different parts of your network are learning at completely different speeds, and that just cripples the whole thing.
So, all of this sounds pretty bad, right? Like a total dead end for deep learning. But, as it so often happens in science, figuring out and truly understanding a huge problem, well, that's usually the first step toward a massive breakthrough.
You see, this whole struggle with unstable gradients forced researchers to get incredibly creative. It directly led to a huge wave of new ideas. Everything from inventing smarter activation functions that didn't kill the signal, to designing totally new kinds of networks like ResNets, specifically built to help that gradient flow. This challenge was the spark that created the entire toolkit for modern AI.
Just to give you one really important example, a huge step was moving away from older activation functions, like something called the sigmoid function. It was super common, but mathematically, it had this nasty habit of shrinking gradients. Replacing it with functions like ReLU, the rectified linear unit, which doesn't have that shrinking effect, was a massive game changer for keeping the learning signals strong.
So, the real takeaway here is this. The vanishing gradient problem and all that learning instability, they weren't failures. Not at all. They were the exact challenges that unlocked the next era of AI. It was only by understanding why deep networks were so hard to train that we got the tools to finally make them work, and that led directly to the deep learning revolution that we see all around us today.
And that kind of leaves us with a final thought, doesn't it? It makes you wonder, what other problems that seem impossible today are we facing in science and tech that, once we really understand them, won't be dead ends at all, but will actually be the very things that lead to the next great leap forward?